Welcome to the lecture on heat affected zone in welding. So, in the last classes we discussed about the welding processes and we talked about the heat flow in welding. Because of the thermal effects, we know that there are many zones which are formed in welding, and the zone which is affected because of this thermal cycling, that is which is of paramount importance, is the heat affected zone, because in this zone there is largest effect on the mechanical properties because of the microstructural variations in certain materials. Normally the material which undergoes the polymorphic transformation, allotropic transformations. So, in those cases you have the changes in the microstructure, because as the temperature stage is exceeded, or as the different critical temperatures are achieved, you have change of the different phases. So, you have the change in the microstructure, and in those materials which does not undergo that type of transformation, you have basically the change in the grain size. So, that also affects the mechanical property. So, basically this heat affected zone is of paramount importance, and this is basically inevitable. You will certainly get this zone. The only thing is that in certain welding process it will be more, and in certain welding process it will be less. So, and also it depends upon certain welding parameters. So, by choosing proper parameters you can try to see that the zone is of minimum area or so that the adverse effect on the mechanical property is minimum. So, that is how the heat affected zones are important in welding. Let us come to the introduction about the heat affected zones. As we know that it is a part of the welded joint which is heated up to solidus temperature of parent material. So, as we know that once you have a zone, then after the weld metal zone, the zone starts which is partly melted. Then after that the zone is the grain growth zone, under bead zone is there. Then you have the adjacent to it is the grain growth zone. So, it has upper and lower boundaries. Then after that you have the grain refinement zone. Further you have partly transformed zone, and so. So, basically if you look at the zone onwards from the fusion zone or so, the maximum temperature is, so a zone is the one which is completely melted, that is weld metal zone. So, that is anyway a recast type of zone. So, where there is complete melting and then there is solidification. But then there are zones where the maximum temperature will be close to that, just below that temperature. So, that is solidus temperature, and then it goes slowly lesser and lesser towards the inner side, and you have the different effect of these temperatures. So, what we see is that you have the maximum temperature which is heated up to, that is your solidus temperature of the parent material. Now, what happens that because of this heating and cooling cycle, you have varying degree of influence. So, wherever it is heated to a larger extent, the effect will be more pronounced, and wherever it is heated to lesser extent, then that effect will be somewhat different. Also, because it is heated very fast, then the retention is for very small time, then further it is cooled at a very fast rate. So, that affects the properties or microstructure of the welded joint in that heat affected zone. So, basically because of this heating and cooling cycle, you have different degree of influence. Somewhere it is more, somewhere it is less, somewhere the grain growth takes place, somewhere the refinement takes place, somewhere we will see that there will be changes in the morphology of certain phases. So, lamellar changes to spheroidal structures, and also all sort of changes take place, and that is what we observe in the case of heat affected zones. Now, the thing is that we are going to see, we have different type of materials which are welded, and you have in certain metals you have polymorphous type of transformation takes place, and in certain metals it does not take place. So, in those metals like copper, aluminum or nickel, that transformation does not take place as the temperature goes up to its melting temperature. So, in those cases you do not get the different microstructure, whereas in the materials like steel or so, you have this polymorphous transformation taking place at different temperatures. As you go above, you have different critical temperatures defined, and you have different phases that is defined, alpha ferrite, you have then austenite, then you have delta ferrite and all that. So, in those cases, as the temperature goes into different zones, you will have different type of microstructures obtained, whereas in the cases where there is no polymorphous transformation, certainly there will be the grain growth, because the recrystallization will be there. Because of that, you will have the change in the grain size, and so and that also affects basically the mechanical properties. Further, depending upon the peak temperature reached in the heat affected zone, you have different subzones formed. So, as we discussed that once you have the different peak temperatures obtained in certain zone, then you have different subzones are defined. Like if you see from the top one, if you look at a typical steel weldment, low carbon steel weldment. Now, what we see, we had referred to this figure in our earlier slide, earlier lecture, where we saw that this is a zone which is the heat affected zone. Now, what we see is that you are heating the material. Now, these are the zone which is heated and completely in the molten state, that is your weld metal zone. So, that is your solidified weld. Now, after that you have a zone that is under bead zone. So, this zone which is just under the bead, that is on the weld just after the weld metal zone where it is getting solidified. After that you have a zone, that zone is normally the under bead zone, and this is basically heated beyond the critical temperature of grain growth, and that will be extending up to the fusion boundary zone. So, you have the fusion boundary zone, and up to that it is heated. So, that zone is known as the under bead zone. Further, so that comes here basically in this zone, the grain growth zone, its upper portion, that is your basically the under bead zone will be there. Then you have coming to the grain growth zone. Now, grain growth zone, as you see, this is in this zone. So, here also grain growth takes place, here also grain growth takes place. This is near the higher temperature side. So, this zone altogether, this is known as the grain growth zone, where the grain coarsening takes place, and you are going to get the coarser grains. So, as you see in these zones, its effect can be seen in these zones. If you look in this temperature zone, which is coming to this side, you see that you have these grains which are coarser, and then this is also coarser little bit, but then that coarseness somewhat decreases once you come to the lower temperature side of this grain growth zone. So, this zone is known as grain growth zone, and here the temperature, if you look at here, this is something close from 1150 degrees C up to the peritectic temperature. If you look at this temperature, so up to that temperature is normally the grain growth zone, and then adjacent to it towards the weld metal zone will be your under bead zone, and you have the fusion boundary zone and all that. So, that is grain growth zone and underbeat zone will be coming in this region. Further, you have the recrystallized zone, or it is also known as the grain refined zone. So, in this zone the recrystallization takes place, and because of that the grains are becoming finer. So, that zone is basically, if you look at, it will be starting somewhere from close to 950 degree centigrade to about 1150 degree centigrade will be the zone which will be basically the recrystallized zone or grain refined zone, and then you have partially transformed zone. So, partially transformed zone, if you look at, now this zone is somewhere, if you look at, this will be in between these two critical temperature zones. So, this will be normally from 750 to 950 degree centigrade, in between the lower and the upper critical temperature lines. You have this partially transformed zones. We will discuss about all these zones, what typically occurs in these zones. So, we will have that understanding about these zones. Then you have the tempered zone. Basically, this is zone of spheroidized carbides. So, here basically tempering takes place in one sense. The temperature is further less, maybe from 550 to 750 degree centigrade. If you look at this zone, this will be close to 550 to about 750 degree centigrade. I mean, the higher temperature is close to the lower critical temperature. So, maximum temperature will be close to the lower critical temperature, that is 723, or it's little slightly more, 750 degree centigrade, and then the lower critical lower temperature limit will be about 550 degree centigrade. So, in that basically the formation of spheroidal type of cementite particles occurs. So, that is why you will tell it as the spheroidized zone, spheroidized carbide zone, that is also shown here as tempered zone. And then after that you have the zone of unchanged base material or unaffected base material. So, here the temperature is not going beyond 550 degree centigrade and there is no appreciable change. However, there will be certain property changes, maybe because of the heating cycle, because of the temperature increase and because of certain type of interaction with carbon and nitrogen of the dislocation movement, and then there is certain type of grain, I mean embrittlement, which is observed. So, because of the dynamic strain aging. So, that is the unaffected base material. So, these are typically the different type of subzones which are found in the case of heat affected zones. Now, the thing is that the final macrostructure of the section of HAZ here, the final macrostructure, it will be depending upon many factors. So, that factors are like the grain size, what are the grain sizes which are formed during that process. Then what is the peak temperature attained, that also is important, because you know how much is the peak temperature. If it is higher, that will be affecting the grain sizes. Normally higher will be the temperature, more will be the grain sizes. So, grain coarsening takes place. Then heating and cooling rate also, how is the heating and how is the cooling rate, because that ultimately affects the transformation products. If you are heating at a very large rate, then conversion may not be adequate from one phase to other, like you are heating to a very fast rate. Then suppose the ferrite or the pearlite structure which you get, now once it goes into the temperature more than 950, once you go into the austenitic zone, then that is to convert to austenite. So, that now if the heating rate is quite fast and if the time is given very less, then the whole conversion may not take place. So, you will have partial conversion. Similarly, cooling also, if you do very fast, then there may be resultant microstructure in different way. that may lead either to perlitic structure or to ferritic structure or to martensitic structure or to benitic structure. So, that again depends upon in what way you are cooling, and that we will discuss depending upon what kind of cooling, what type of structure we get, that we can discuss later when we talk about the heating and cooling cycle, maybe in terms of heat treatment cycles. So, this is the different zones of the weldment which is there in the case of heat affected zones. Now, the thing is that when we talk about the heat affected zones in welding, now what we see that it is nothing but the heating and then further cooling. So, similar to a heat treatment process. So, we can say that it is type of heat treatment process, but then when we talk about the normal heat treatment process and when we talk about the thermal cycling or thermal treatment which is given in terms of the welding process, it has altogether a different meaning. So, that differs in many sense. The point over which it differs is that when we talk about the welding, then the maximum temperature which we get is close to the solidus temperature, whereas when we do the heat treatment, if we tell I mean with reference to low carbon steel or so, in that case the maximum temperature which we go for the heat treatment process is normally very small. We go to 950, 10 or 1000 degrees centigrade. So, or 1050 degrees centigrade. So, the maximum temperature which is achieved in the case of heat treatment is normally very small, whereas the maximum temperature which you achieve in the case of welding is quite high. It goes to very high temperature of around the 1400 degrees C or so, where it is the solidus temperature is there. So, you have that is the one of the major difference. Then the thing is that there are two things which occur in the case of welding. In the case of welding, you heat at a very fast rate. So, because the heat input is by external source, and this source either by using the arc or by using the flame. So, this heating rate is quite fast in the case of welding. So, it takes very less time to reach to that peak temperature, whereas in the case of heat treatment, we do not heat that fast. We are heating at a slow rate. We can heat at fast rate also, but we can also heat at slow rate. Normally, it is not that fast. We are heating in a furnace normally by putting in a furnace where the heating is not so fast. So, the heating rate is normally very high in the case of welding processes, whereas it is less in the case of heat treatment processes. Then comes the retention time. Now, if you talk about a typical heat treatment process, then what are the things? One is that you are heating, then you are retaining, and then further you are cooling. So, in a normal heat treatment process, you are heating first and then you are this is retaining and then you are cooling. So, this is typically in the case of heat treatment, where you will have you go little bit, this is your lower critical temperature. So, you go above that, maybe close to 950, 1000 or so. Now, in the case of welding, what you do is you heat, but you heat very fast and then you come very quickly. You do not retain. So, retaining basically is very small retaining time. So, what you see is that the retaining time is very small here. This is the retaining time in case of heat treatment, and this is the retaining time in case of welding. So, in welding what you see that you are going to melt and quickly it gets solidified, and you are not holding it for time, whereas you are holding it here. During the holding, basically there will be transformation of one phase to other uniformly, and then further you are cooling slowly. whereas in the case of this you have very fast cooling, you may have little bit moderate cooling also, you can control it somewhat, but then this way, so this is close to your melting temperature, and this is your this is something close to 950 to 1050 degrees centigrade. So you see that the higher temperature which is achieved in case of welding, and here this is your heat treatment cycle. So this is the basic difference between a welding cycle and a heat treatment cycle, and that is why there will be associated changes in the microstructure, and once you have the associated changes in the microstructure, then you have changes in the mechanical properties, and so that is the basic difference between these two. So basically the heating rate as well as the retention time, and then also the cooling rate also may be different. So because of that you will have the different properties of the, and that is why you can say that the heat treatment as well as the welding have some different end result in that sense. Now we will talk about the different type of zones which we see. So first of all we will talk about the underbeat zone or the grain growth zone, which is underbeat zone will be just below that fusion zone, next to the fusion boundary zone, and from there the grain growth zone starts, and then we come to the that whole grain growth zone, and after that you will have grain refined zone. So we will come to the first zone, that is grain growth zone. Now as we know that the grain growth zone, as the name indicates, here basically there will be the growth of grains. So it will be lying next to the fusion boundary zone. So as we see, you have this fusion boundary zone, just below that you will have this grain growth zone. Now it undergoes the austenitic transformation and grain growth. So as the temperature goes, you will have crystallization started at certain temperature, and then once you go to the larger temperature zone, you will have grain growth started. So that basically increases the size of the grains. Now degree of grain growth will be depending upon the chemical composition and specific heat input in the welding. So normally what happens, that the critical temperature for grain growth is normally about 1050 degrees centigrade for structural steels. So above that you will have the grain growth starting, and for certain type of materials, for certain kind of specialized steels like microalloy steels, where the grains are even smaller, that temperature may be close to 1300 degrees centigrade. So after that the grain growth is more predominant. So in that case, that is why the grain growth is becoming important, and that is why it is depending upon certain type of composition and then also the specific heat input in the welding. Now what you see is that depending upon the type of process also used, you will have these grain growth observed differently. Like the shielded metal arc welding, you will have a smaller grain growth as compared to the submerged arc welding. And if you look at the electroslag welding, it will be even higher grain growth, which is observed in the case of electroslag welding. Now grain growth is basically very important parameter, because it is affecting the properties in the sense that it will be decreasing the zone plasticity. Once you have the zone growth, growth of the grains, then it will be decreasing that zone plasticity. Then susceptibility of steel to cold cracking and stress relief cracking will be increased, and also the metals which are not undergoing the polymorphic transformations, that may be lowering in the strength. So that is one of the reason why this grain growth is detrimental for the material. Then the next zone which comes is the grain refined zone. So, as we see that after the grain growth zone, you will have grain growth zone as we see from 1150 onwards. So, below that you will have the grain refinement zone. So, for the grain refinement zone, the maximum temperature is 1150. Now, from 1150 onwards you have the grain growth zone, and from 1150 below you will have the grain refinement zone, and it will be starting from 950 about degree centigrade. Now, what happens that it does not exceed basically 1150. So, that is the maximum temperature. Now, in that what happens that once you go from 950 above, then the alpha to gamma transformation takes place, because ferrite is not stable. So, that will be changing to the austenite, and that is ferrite to austenite transformation will be during the heating, whereas the austenite will be transforming to perlite when it will be cooling. Now, as you increase the temperature from it goes above the 950 or so, then you have the ferrite to austenite transformation, and then it does not get, if it does not get the enough time to develop properly, because temperature is somewhat lower in that case. So, you will have basically the grain size remaining smaller. So, because of the not achieving that very high temperature, that grain size becomes smaller in this case. Similarly, when you come to the cooling cycle, that is the reverse cycle, now in that basically gamma will be transforming to alpha. Now, again that will be making the finer grained ferrite, because the temperature is lower. So, that way fine grained ferrite structure will be obtained, and ferrite perlite mixture may be obtained, ferrite perlite type of structure will be obtained, depending upon again the heat input parameter, or like plate thickness. So, based on that, because that will be affecting, that will be basically judging the cooling rate or so, which will be experienced by the specimen. So, based on that you will have different type of structures, either so you may have ferrite perlite type of structure or so. So, what happens that in this zone you have the grain refinement being taking place. So, now the thing is, one thing is to be understood, that once you go to the temperature above this upper critical temperatures or so, once you go to above that temperature, if you retain it be there for larger time, then that case also, for if you stay for long, that also increases its size. So, grain growth will take place. Further, if you are going to higher temperature, grain growth takes place, but if you go and do not retain much time and then further come down, then in that case the grain growth chances are normally lesser in those cases. Now, next will be your partially transformed zone. Now, in the partially transformed zone, the temperature is normally between 750 to 950 degree centigrade. So, normally it is between the lower critical to upper critical temperature. So, if you look at this figure, it is this is the lower critical temperature and this is the upper critical temperature. In between you see that this is the partially transformed zone which is observed. Now, in the case of partially transformed zones, what happens that when you are heating, so you are not going to very high temperature. Now, in that case, once you starts cooling, then in that case the while heating perlite will be trying to get dissolved. So, first of all the perlite will be dissolving. So, perlite will be transforming to austenite, because once it goes from 750 to above, that is lower than more than the upper this lower critical temperature. So, basically as you see that, so once it goes from here in this zone, all this, so perlite which you have otherwise, it will be transforming to austenite. So, that transformation will be taking place through nucleation and growth. So, that takes, and now since it occurs through nucleation and growth, we require certain minimum time for it to take place. Now, but as you finish this process at 950, so you do not get much of the time for the full transformation to take place. So, further you go for the cooling. Now, once you go for cooling back, then what happens, the reverse transformation does not lead to the lamellar type of structure, rather it gets the rosette type of structure of the perlite, and that rosette type of structure is known as the chunky perlite. So, either your rosette structure of perlite or you have the chunky perlite type of structure is formed. Also, this is, treatment is done in between the lower and upper critical temperatures. So, that is also known as intercritical type of annealing treatment or so, that we will see later. Now, in that case, depending upon the cooling rate, you may have the martensitic type of structure because of that sudden cooling, and because it goes from here and it is cooled. So, you get even the martensite type of structure, and you get dual phase steels which have a very good combination of properties, strength as well as ductility, and if you have very you can have such properties used for specific applications also, like in the nuclear energy applications also it is used. So, you may have also the possibility of obtaining upper magnetic and martensitic type of structures. Then comes the zone of spheroidized carbides. Now, this zone, basically here the maximum temperature is going up to from 550 to about 750 degrees centigrade. So, here what happens that you have it is just the extension of that partially transformed zone. So, you have the reduced occurrence of the chunky perlite, and what happens here, that here the cementite, which is the otherwise in lamellar state, that comes to basically a spheroidal type of structure. So, that is agglomeration at the grain boundaries as well as at the triple junctions which are found, and they will be black in color. So, you will have the spheroidized type of carbides are formed, that is why it is known as zone of spheroidized carbides. So, that way you have that zone. So, then you have, after that you have the zone of unchanged base material, where you have, because of the dynamic strain aging, you may have some change in the properties like embrittlement or so. Now, why it is important to discuss about the properties of HAZ, that because of this HAZ you have some change in the properties, especially toughness. So, there is decrease in the toughness in case of HAZ, and as the toughness decreases, you have that is very desirable property. So, now because this is because of many reasons, and the one of the reason is because of the aging treatment below that lower critical temperature, also due to the grain coarsening in the underbeat zone where it takes place. So, that grain coarsening decreases the toughness of the material. Then you have the decrease of the corrosion resistance also, that is stress corrosion cracking may be observed in the case of the lowering of the toughness, or in the case of these HAZs, and especially in the presence of sulfur compounds like H2S or even Cl2 or alkalis, you have this stress corrosion cracking is seen to occur in the case of HAZ, especially in the underbeat zone. So, this is how this HAZ is an important domain which must be kept into mind while we do the welding operations, so that the effectivity of process is maintained. Thank you very much.